Essentially, this is a chapter that we started with. This notes, I think, available for you. So we look into the problem of what is called the Hamilton's principle. Essentially, this principle is based on the calculus of variation. Okay, calculus of variation. Essentially, you are minimizing a functional which depends on position, and then the velocity and in time. Okay, so this f function is now Lagrangian. So having done this calculus of variation, you want to optimize this. So this led us to the equation of motion based on Lagrangian, that is based on q for every variable, and then you have a d with respect to time, and then the Lagrangian, which is with respect to the velocity. Okay, so this is the equation motion that we need to solve. Okay, so we need to solve, and we know there's a Lagrangian function. This very important Lagrangian function essentially is the kinetic energy minus the potential energy. Okay, so we have actually looked into it, and we solved some scenario problems. Essentially, we realized that what we need to do, the important points that we need to do is identify the system's coordinates. So we need to know the generalized coordinate. Okay, generalized coordinate, which is the q case and then the respective velocity terms. Okay, once you know these, then you go to write the kinetic energy in terms of the velocity, and then the potential energy in terms of generalized coordinates. Okay, once you get that, then you determine the Lagrangian, which is kinetic energy minus the potential energy. Okay, once you get this, the question now is going from the Lagrangian and then to write down the equation of motion. Okay, all right, so that's what we did, and then we came up to this point. Okay, so we have actually reached out until the Noether's theorem. So all this up to here is actually part one, which we discussed last week. Okay, so this week, today, we will look into a second approach based on the Hamilton's principle, but then this is based on the total energy. Okay, so this is energy difference. Lagrangian is based on Lagrangian here is the energy difference. Okay, so the Hamiltonian essentially is kinetic energy plus the potential energy. Okay, so this is the total energy that you have seen, and you have used Hamiltonian in your quantum mechanics. Okay, so you realize the Hamiltonian essentially is an operator in quantum mechanics, and the eigenvalue of Hamiltonian operator is the energy values, okay, of the system. So essentially, the language is beginning to be more universal, easy to move from classical dynamics to quantum mechanics, from classical mechanics to quantum mechanics to quantum field theory, which is used to to construct the theory of fundamental forces. Okay, so it's a very powerful route. Okay, so in Hamiltonian mechanics, we need to look at just like the Lagrangian equation. You need to find what is the equation of motion based on Hamiltonian. Okay, so these two canonical equations, q dot, there's a q dot, and then okay. So again, my computer is going disconnecting. So let me just go back to the mirroring. Okay, I have to move from one to another. Okay, let me just quick sharing, and then we come back to the sharing again. Okay, so this is the canonical equation that we need to derive. Okay, and you can see the Hamiltonian enters from here, and then Hamiltonian enters here. And finally, we will we'll look at one interesting quantity called the Poisson bracket, okay, which is the classical correspondence to the commutator rule, okay. So in quantum mechanics, in QM, you will see this bracket actually is the commutator, okay. All right, commutator relation. So classical mechanics somehow is the departure point for quantum mechanics, okay. So without classical mechanics language and the foundation, quantum mechanics theory and the mathematical structure wouldn't be as it is, okay, if not for the language developed in the classical mechanics. So this one you guys have to appreciate. All right. Some of you have done quantum mechanics and now doing classical mechanics. So I think that's a bit strange, okay? Because you already climbed up and now you're coming down to the basement where the foundation is. All right. So let's start with the Hamiltonian. We look at the, we have done this. I'm not going to repeat here. So quickly we go to the part which we left in the last lesson, which is the Noether's theorem, okay. So I hope some of you, not all of you, would like to even bother to to look into the historical development of theories. So if you really want to appreciate the extent of contribution of Emmy Noether, you should go and explore the historical background around this the brilliant mathematician. And you will appreciate, the both side of how much she has to suffer for of her time when things are not in favor of women mathematician. At the same time, her work is now being recognized as the backbone of all fundamental theories. Okay, so symmetry is the fundamental property of physical laws. And it is based on Lagrangians, and then go and find out, read about the biography, maybe, the background search, so that you appreciate this law, this, this theorem, and also it's important for physical laws, okay? So today, let's move to the main point, all right? Let's move to the main point of Hamiltonians and canonical, equation of motion. Okay. All right. So let's. I'm actually, using the hotspot from the iPad to go to my workstation because UM's Wi-Fi is not working. Okay. So let's just let's try to make this thing work. Okay. Okay. So so today our discussion main point is look at Hamiltonian. All right. Once again, you need to know that you need to understand kinetic energy and also the potential energy. Okay, you have to determine for the system with the correct. Okay, so once again you still have to look at the system. You have to examine the system and decide the Q's. Okay, and also the Q dots. Okay, which is the velocity, generalized velocity. Once you decide this, you have to determine now from this Q, there is a kind of switching between this Q and then the momenta. Okay, this is the momenta that we are looking at. This is the momenta that we are writing here. Okay, so the connection between these are achieved through this relation. Okay, this relation is the relation between the Lagrangian and the velocity. So you still have to derive the Lagrangian, okay, like it or not. You still have to derive the Lagrangian, because Lagrangian is just the minus of this. So remember these two, okay? Remember these two. Both of them are involving T and U, okay? So you can derive in principle the Hamiltonian just by summing the kinetic energy and the potential energy, okay? But there is one intermediate step. You notice that Lagrangian will depend on, if you compare, Lagrangian depends on position, which is qk, and then the velocity, which is the q dot and t, okay, if there is t. But Hamiltonian will depend on position and then the momenta, okay? So you need to write down the position and the momenta, but the momenta is related to is determined based on this expression, okay, from the Lagrangian. All right, so you still need the Lagrangian in order to determine the generalized momenta, right? And there is a relation that connects the Lagrangian and the momenta, okay? So there is a relation between these two, which you can actually go through the notes textbook to actually find out how this is obtained. All right. Essentially, this is obtained based on the equation of motion, Lagrangian equation of motion, and also the conservation laws that relates to the kinetic energy, total energy. Okay. So you still need to decide. You still need to decide what's the Q. Once you get this, second step is to determine the generalized momenta based on the Lagrange. So before that, you need to find your Lagrangian. Okay. So you need to determine the Lagrangian as a function of Q, K, and Q dot K. Okay. Once you get that, step 3 is to determine, to prepare all the momenta that you need for every, okay, for k equals to 1 to up to any point, okay? So you have to find out what is the momenta for every coordinate system. Once you get this P, then you can calculate this quantity. Either you write down your kinetic energy in terms of P and you plus with Q, or you can use this relation once again. So you can write down with the Q dot K minus Lagrangian and then change the Lagrangian into, okay? So you have to change this variable using this relation, okay? All right, so that is the idea, okay? So so that is how you determine the important quantities. Okay, I repeat, you need to know your generalized coordinates. You need to still determine the Lagrangian. You need to determine the generalized momenta, and then you have to determine the Hamiltonian. Once you get the Hamiltonian, you can go on and derive the equation of motion for the Hamiltonian. Okay. So how this is derived, I just showed you in these notes, so you can follow the argument. I will quickly just explain. First, we assume that the Hamiltonian depends on it depends on position, it depends on and momenta, and depends on time. We assume. So any change in Hamiltonian will be the sum of changes that comes from H due to Q, and then change in the H due to P, and the change in the H due to the time. Okay, so there are 3 changes. This is calculus, right? So this is just, you have any change come from the change due to the Q plus change due to the P plus change due to the temporal change, okay? Temporal change. So that is just the total change. And then you also look at the change that comes from the equation that we relate here. Okay, the equation that we relate here. Any change from this particular quantity here, any change in this particular quantity must come from change from this and change from this and change from this. That's why you have a this expression, and this expression. Okay, combining this, comparing these two. If you compare, okay, so if you just happens to compare these two, if you compare this term, you compare this term, if you compare this term, so this is where you obtain the equation of motion that I underlined here. Okay, so the equation of motions now becomes two. You have two first order ODE. In Lagrangian, you have one second order ODE. Okay, that's the difference between the Lagrangian dynamics and the Hamiltonian dynamics. Okay, all right. So you guys follow? Is any questions? Okay, so the toolbox in our perspective is, you need to know how to calculate Lagrangian, you need to know how to calculate momenta, you need to know how to calculate Hamiltonian. Once you get the Hamiltonian, you write down the equation of motion, which is based on these quantities. Okay, based on these quantities. All right. So that is your equation of motion. So this is a mathematical logical route. Therefore, you need to know the steps. What are the mathematical steps? Okay. So the problem is very much procedural. So you need to calculate this. And this is called the canonical equation. Why it's called the canonical equation? Because it connects the coordinates and the momenta. Okay. These are conjugate quantities. So the symmetry that we mentioned here is, if you look carefully, okay, so if you look carefully, this quantity first is the position, the change of position. Okay, so the change of position here is connected to the momenta, and then the change in momenta is actually related to the position. And then you can see that there is a correspondent in this direction, and then there is a correspondent in this direction. The symmetry is quite interesting in terms of the way it sits. All right. So it's a very nice mathematical structure. You ask why there exists such a structure in the representation of the system. If you go deeper into the symmetry and conservation law and mathematical property of Hamiltonian, then you will know that even in quantum mechanics, you see this symmetry, okay, in terms of Hermitian properties and so on, okay. All right. So now let's look at the problem solving scenario so that you get this idea clear, okay. Let's look at the problem solving scenario, okay. First, let's consider the example here, a particle of mass m. So the particle is here, okay, of mass m, move on a smooth surface. That means there is no friction, okay, on a cylinder, interior part of the cylinder or exterior, doesn't matter, okay, in a cylinder, and is subjected to a central force. So if you know central force, it is originating from the origin here. Okay, so that is your R. And the question says, in fact, it's helping you to find what are the things you need to find. The Lagrangian, the Hamiltonian, the generalized momenta. Once you get that, you can write down Hamiltonian and the equation of motion. Okay, so let's start the steps. Step one. Okay, step one. So that's a step. Okay, we want to look at the steps. Step one, you need to know what is the coordinate system. Okay, you need to prepare all these coordinate system. Step two, you have to determine the Lagrangian. Once you get the Lagrangian, okay, it allows you to determine the P as well. Once you get the P, so you can determine the Hamiltonian, number 3. This is number 3. Okay. So number four is the equation of motion, EOM, equation of motion. Okay. So let's look at this problem. The coordinate system. First, the coordinate system is, because the motion is described from this graph, you can see from this picture, it is a radial, and then it is moving on a cylinder. So the cylinder is given, therefore is a cylindrical coordinate system we adopt. Okay, we adopt cylindrical coordinate, and since the cylinder has the constant radius, okay, so the radius r, that is the r here, this r, okay, is a constant. All right. So you have theta and z that will be acting as the free variable. Okay. So wherever you anticipate that there will be a two equation of motion that we will have to determine. Okay, for the theta and r. And we also look at the constraint, because r is fixed, therefore z and r now is connected. Okay, all right. So this r actually is a third coordinate system which is not part of a cylindrical coordinate. So the small r is not a part of the cylindrical coordinate. The capital R is the part of cylindrical coordinate. Okay. But because it is moving under the central force, therefore we need to find out that small r in terms of the capital R and Z. Okay, so that you have this constraint that comes in. So you can write down the kinetic energy now in the cylindrical coordinate as this. Okay, and R is not changing, therefore you only have the first two terms. So you have only these particular terms. Okay. So you only have these two terms, these particular two terms. And potential energy depends on the central force, and you can quickly determine this is the elastic force. So you have the elastic harmonic energy, okay, harmonic potential. So you have the harmonic potential, and therefore replace the small r in the coordinate system that we need to define the cylindrical coordinate. Okay, these two. So once you get your T and U, you have your L. Okay, and write down your L, and you can determine your generalized momenta. All right. So now this question didn't say about gravity. Okay, so as if the problem is being solved in a free space. Okay, but if the gravity comes into the picture, so you can see you need to add the mgz, okay, for the vertical force. If there is a force in this direction, so this is if there is a g, okay, if there is a g. But in our case, the question, we didn't say that. Okay. All right. So once you get these two, once you get, let me just go to that. Okay. Once you get your generalized momenta expression, you determine the generalized momenta for the angle, because you have two angle and then z. Okay. So you need to determine for these both. So that is the generalized momenta for the angular variable. This is a generalized momenta for the z variable. Okay. So now you already have this. Okay. So we already have our momenta ready. Once you get the momenta ready, therefore now you can determine your h. So you have your h calculated, and you can once again quickly determine what is the kinetic energy return in only the momentum and the coordinate system. So that's the thing. And that's the reason why we need these two expressions, okay? This expression will be used to replace the velocity. So the velocity and the momenta will be related here. So you use this to replace, okay? To replace the two terms that I mentioned just now. Okay? So now you have your Hamiltonian, which is only in the term of momentum and the position. No velocity term here, you see? No dot quantities here, okay? All right? So we determine the Hamilton's equation of motion, and for the angular variable, that is the velocity, equation of motion, and then the moment for the momentum. So these two conjugates, these two are called the conjugate or canonical equation, and for Z you have these two, okay? And again, you can look for any conservation quantities, especially when your Hamiltonian, you take a derivative, you get zero, that shows there is a conservation loss, okay? Because it does not change, with respect to the coordinate system, okay? So the angular momentum is conserved, all right? Okay, so this is the equation of motion. So likewise, if you write down this equation in terms of, do a little bit algebra, you see there is a simple harmonic motion in Z, meaning the particle, because the particle is moving in a cylinder, let's say this is your original coordinate, there is a force, and the force actually is depends on R, and the force is kr. So the particle will actually move in this direction, okay? It will just oscillate. It will keep oscillating in this direction, okay? It will be oscillating in this direction on a thing, and that is reflected by the simple harmonic motion in Z, okay? So it will be moving in the Z because of this elastic force that actually hold the particle here, okay? All right, so you see this is the way we solve this problem, all right? Determine the coordinate system, calculate the kinetic energy, potential energy, determine Lagrangian. From the Lagrangian, determine the generalized momenta. Once you get generalized momenta, you can write down the Hamiltonian H. Once you get the Hamiltonian H, this one, you can determine the equation of motion for Hamiltonian, called the canonical equation of motion, okay? You can solve it if you can, or requested to solve, okay? Any questions so far before we go to one more example to illustrate these points? Are you following the procedure? Is it all right?
Yes, Professor.
Okay, so we go for one more example just get us used to the line of reasoning, okay? So we look at one more example, arbitrarily chosen is a spherical pendulum, okay? Which straight away it requires the quantity like R, you need a quantity, a coordinate system of this kind, R, theta, and phi, okay? So because it's a spherical pendulum, all right? But then some quantities can be, curved or, made to go to zero because it's not changing. It won't appear in the equation of motion. If it's on the fixed radius, for example, the fixed radius, so this fixed radius will be the capital R. So it's becoming a constant. Therefore, there won't be an equation of motion for a constant. So ultimately you only have these two as the equation of motion. Okay. So you must read the question properly to find out what is a constant variable. Somehow camouflage in the question by a statement, fixed R. but you know you can have a pendulum actually on a flexible rod which is extendable. Okay, so you can also have a flexible rod which has elasticity. Okay, so in this case it is not, it's a fixed radius, means it's a rigid rod. Okay, now the question asks, what is the suitable coordinate system? Okay, so the suitable coordinate system is, as the question goes, is a spherical coordinate. Okay, spherical coordinate, that's the original, but because r is fixed, therefore reduced to just 2. From 3 variables become 2 variable. It solve the problem, simplify the problem. Now question 2 says, ask, determine the Lagrangian. To determine Lagrangian, you need to find what is the kinetic energy. And in a spherical coordinate, the velocity term is this. And since r is fixed, the r dot becomes 0, and therefore left with just the 2 terms. Okay, small r become capital R, which is a constant. Okay, then the potential energy, it is rotating in a gravitational field, assuming. Okay, you can ignore that, then you won't have the gravitational potential. Okay, but in this case it didn't say explicitly, but the diagram shows there is a G. Okay, and the kinet, and you can set the reference point arbitrarily anywhere you want. So we set at the midpoint to be 0. So the potential energy now is written in general as the mgh, and the h is actually the r cos this particular distance. Okay, so that is the r cos this particular rod, this length, that is the r cos. Okay, so that's your angle, this is your r, and therefore this is the cos, r cos. Okay, so you have that. So now the Lagrangian is written, and Lagrangian now involve the velocity term. Okay, that's a velocity variable which we have to get rid of in terms of momenta. So again, what is the general momentum or generalized momenta? Because of 2 variables, therefore you have the 2 momenta. The momenta with respect to phi is theta is this, and then you can calculate quickly from this term. Okay, this term, so you get that, and then this is depends on phi. Okay, so the phi is based on this term. Where is phi? This is the phi, so that is the depends on phi, right? These 2 terms, this for the theta and this for the phi. Okay, and you can prepare the velocity term just to simplify your future work, because you already calculate this. So you prepare, okay, you prepare to change this variable using this variable. Okay, so that's why we are writing these 2 expressions here, so that we can change. Once you have these, you can now write down your Hamiltonian. So that is the Hamiltonian written both ways, either like this or using this equation. So you can determine the first term due to the theta and the second term due to phi, and then plus your potential energy. That's your potential energy. Okay, so where's the potential energy? Here. Okay, so that's your potential energy. So now you have your Hamiltonian. Once you get the Hamiltonian, you go for equation of motion for the 2 variables, okay, 2 angular positions, and then they have a pair. So you have the theta dot and p dot, okay, theta and p, the position and the momenta for each. So these are quite straightforward, derivatives from here. So the equation motions can be written quite, without much complication. Okay, unless the term requires you to refer to table of derivatives, otherwise it shouldn't be a complicated scenario. Okay, and then you can check for if the quantity is 0 like this, and the momentum in phi is conserved. Okay, in that angle is conserved. So that's a conserved quantity. Okay. All right, so you can carry on and check out how does we can manipulate the scenario using all sort of going from Hamiltonian to Lagrangian, Lagrangian to Hamiltonian using this example. I won't explain this example because it's just a variation of the theme. All right, okay. So basically, the list goes on for any. Okay, so I'll just recap. For any system. Okay, system, you have to identify the QK. Okay, there could be many. Identify the QK. Look for constraint. Okay, constraint. Why look for constraint? It can help to reduce number of QKs to solve. Okay, example, fixed radius. It is oscillating with a constant angular velocity. All these statements are actually telling that you can reduce the number of variables. Once you get these, so once you then that will allow you to will point to a suitable coordinate. Okay, suitable coordinate system. Okay, so typically you have Cartesian, so you have polar, you have cylindrical, you have the spherical, at least the Euclidean. Okay, these are all the Euclidean systems. So you have this, and then you have this, and then finally you have this. Okay, all these three. So for each of these, what is the position, what are the position, and what are the velocity terms. Okay, so you need to know. So this is the velocity in respective coordinate system. You need to know. Why we need to know this? Because your kinetic energy is a function of velocity. So therefore, the velocity will take the coordinate system. And why we need to know this? Because the potential energy is a function of the QK. Okay, and this is a function of Q dot. Okay, once you get that, you look for what is the Lagrangian. T must be written in the Q and Q dots, not just Q dots, Q and Q dots. Okay, there could be Q there. And then the potential energy is always with Q. If it depends on time and Q dot, it is not a conservative system. Okay, so there is also additional methods to solve. We call non-holonomics and so on. Okay, so we won't go into that detail. Once you get these, you can actually calculate the generalized momenta by taking the derivative with respect to Q dot. Okay, Q dot. So once you get this, you can write down your Hamiltonian as a function of, okay, T plus U. So then you have your Q dot, which is the derivative with respect to PK, and then the PK dot is a derivative with respect to QK. Okay, dot. Okay. There are ways to remember this equation. There are tricks to help your brain to remember the order of this equation. Always remember position Q, position come first, then momentum. Remember that. So Q must be written first, then P. Okay. So if you write Q, and it is written in terms of derivative of the momenta. So at least Q must be related to P. Okay. Q must be related to P. But momenta, If you want to relate momenta to position, it's almost like going backward. Therefore comes the negative sign. Okay, because it's like from P you want to go to Q, it's almost like going backward. So the negative sign comes. So this is how we remember. Okay, remember the formula and not to miss out the negative. Which one has the negative? Which one does not have a negative? Okay, position comes first and then momenta. Then you write down. Okay, they are P dot means relate to Q. Q dot means relate to P. Okay, then the negative sign comes for the P, which is P. If you want to P dot relate to Q, is a kind of going backward in order of variables. So you have negative. Okay. Okay. So I think we have basically, see the general trend of problem solving for Hamiltonian. All right. Very procedural. It's if you follow this cookbook recipe of solving what to solve after the other, I think you can solve Hamiltonian problem. Okay. The complexity comes when your system is, very, involved in the motion. The constraints are complicated. Then you have to really imagine what variables are needed, what are the constraints. Okay. Other than that, the Lagrangian, the Hamiltonian, the conjugate momenta, all are prescription based. Okay. So finally, I would like to just quickly touch on the Poisson bracket. I won't go into the detail because this part, it's good to know. It's important, very important for going into quantum mechanics. But in a classical mechanics, it is just to say the structure exists. Okay. The structure exists prior to even knowing quantum mechanics. Okay. So this is related to the phase space. If you have taken statistical mechanics, statistical physics, or you are taking statistical physics now, you know how important is phase space. Okay. How important is the phase space? So okay, so phase space essentially is the coordinate system or the P and Q. Okay, so phase space essentially talks about this. Okay, and we did mention in some of the lessons before. If you look at yourself now, you exist in a phase space. Okay, your position and momenta will define where you are now. Okay, whether you are at rest or you're moving around. Okay, at your home. Okay, so if you are moving around, we know where you are and what velocity you are, and you cannot suddenly disappear from this space, this universe, unaccounted for. Okay, it may happen someday. We all live, but you are going out of the physical phase space to another space. Okay, so as long as you are on Earth, people know where you are and what's your kinematics, whether you are moving or you're staying put. Okay, if you are staying put for too long, means it's not a good news. Okay, so you are mobile means you are alive. Okay, so essentially you see phase space defines the state of mechanical system. Okay, so this is a very powerful concept which can generalize to a generalized momenta P, K and QK. Okay, so PK and QK essentially talks about the phase space. The flow of phase space means is the kinematics or dynamics of your particle in time. Okay, so the concept is a little bit like fluid dynamics, but it is about mechanical system. Okay, so the Hamiltonian, when we write down unconsciously, you are writing it in phase space. Okay, So your Hamiltonian, because in quantum mechanics, Hamiltonian defines everything. Okay. So you start by specifying your Hamiltonian for the system. You solve Schrodinger equation, and in mechanics, you write the Hamiltonian. You solve the equation of motion. Okay. Or you solve equation of motion to determine the total energy. And if it's conserved, then the Hamiltonian is a conserved quantity. Okay. All right. So you can make an argument similar to phase space, phase space as we did in many different fields, that it become like a density points that flows. Okay. So if a particle actually at some point here and later time actually have evolved somewhere, it has moved in a phase space. Okay. The trajectory is really define the phase space. So now, if this trajectory are seen as a number of the various points in the phase space, many collection of points, therefore we can talk about density of states. Okay, so you have density of states which is defined by rho. So that is your density in the phase space. Okay, it depends on position qk, it depends on momenta. Okay, depends on the momenta and also may change with time. So any small change in the rate of change of density of space comes from density of change, density change in Q, density change in P, and then density change in time. Okay. So we can now use our this expression now. This expression can be nicely, neatly packed in terms of a bracket that we write down here. This is the expression that actually we expanded. So compressed as a bracket, but actually this is the term that we are writing here. Okay, that's the term. So now your density equation follow a very interesting equation of motion for the total phase space motion. Okay, and this equation is called the Liouville theorem. Okay, and this is the Liouville theorem, a very fundamental theorem in physics. That is the Liouville theorem. All right. So you remember how we actually use the equation of motion from the equation, Hamilton equation of motion here. We have used this. Okay, so we have used this tool to replace this particular expression here. Okay, so we are using that to change these two expressions. Okay, we are using this to change these two expressions. So that leads us to the Poisson bracket. That is the Poisson bracket. This particular quantity is called the Poisson bracket. Okay, with the Hamiltonian here. All right. So you can check it out, the property of Poisson bracket. I don't want to actually go and into these details over this online. So the Poisson bracket actually are defined just now by this any for arbitrary, not just f, for arbitrary quantities can be defined in this form. You can see it's a cross. First you define on Q and then you define on P. So when you define on Q, you have the other one defined on P. Okay, so it's a kind of a cross. When you have Q, it depends. The other one goes by P. When you have the P, it goes by the Q. Okay, so it has this kind of cross structure, and it follows the typical laws of algebra of commutator. And then particularly if you happens to if you look at this equation, this particular equation, all right, if you look at this particular equation, when density is not changing over, it is not changing with respect to time explicitly, then you have the conservative system defined by the Hamiltonian function. Okay, so in that case, you can actually write down Hamiltonian equation as a part of commutator relation. Okay, all right. So this is a very interesting and important, departure point for quantum mechanics. All right. So this equation is called the Heisenberg, representation. Okay. This is Heisenberg equation of motion for quantum mechanics. All right. And this Liouville equation also is very important for quantum mechanics in a in a dissipative setup where the density change over time. Okay. Otherwise, you don't have this particular expression goes to zero. Okay. So basically, that's what I want to discuss related to this chapter. Okay. So we have quickly gone through this few important concepts. The most important one is the Hamiltonian, dynamics. All right. So that's the most important, and then the problem-solving scenarios. Okay. And for just to look at the why Hamiltonian dynamics is favorable for quantum mechanics and quantum field theory is because it has a structure that can be extended to all languages of classical T and also the quantum setting. Okay, that's why it's quite important. Okay, so any questions? Any queries or questions related to this this particular chapter?
Doctor, I just want to reassure myself. The Liouville equation is applied only when the volume.
Yes. Repeat the question, please. The question somehow lost.
I would like to confirm. Is the Liouville equation?
Yeah.
Is applied only when the volume density of the system is constant.
The volume is constant. In that case, you see the d rho dt. D rho dt. If the density is not changing explicitly with time, okay, then the Liouville theorem will be reduced to the Hamiltonian equation. Otherwise, this generic theory, this is quite generic, is used for dissipative system as well. Okay, so it is generally valid for systems that the volume is not fixed and the system can dissipate, meaning the particle can leave the system. Okay, that's why you have the d rho dt. Only when you actually set that to zero means conserve quantities, conservative system. Okay, so we use Liouville theorem even for the dissipative quantum mechanics. All right, we call the open quantum system. Okay, all right. And then when we talk about volume here, this is a volume in the phase space. So you see, this is the volume that we are writing up. This volume consists of dq dp. And you know, each of them is a k parameterized by k dimension. So essentially it's a hyper volume, hyperspace. Okay, not the volume xyz. This is a phase space volume. Okay. All right, so in general, you already have this general statement depends on Q, depends on PK, and also may depends on time. All right. Okay. Any other questions? Any other questions? So we have concluded this chapter, we have concluded this Lagrange Hamiltonian dynamic chapter. If you want to extend this problem further, discussion on this, it will involve constraint are added. You have added constraint, and then we look at the force or constraint, that time evolution. So you solve the problem of Lagrangian and Hamiltonian that depends on on time. Okay, so the problem becomes slightly more involved, but that is just the adding complexity. Okay, by having constraints, that time dependent constraints and so on. So when we actually put Lagrangian and Hamiltonian, which is not time dependent, so it becomes conservative, simple conservative system. Okay, the total energy does not change, right? So even in your QM also you solve Hamiltonian, which is time independent, right? When it becomes time dependent, so you have to bring in a perturbative theory and so on. So time dependent will bring more complexity to it. So that can be explored when you go deeper at a graduate level, or even you work on FYP that talk about that kind of system. But for the general introduction to to most of us, for the course, I think it's enough for us to know, at least for the case of time independent Lagrangian and Hamiltonian. Okay, and non-dissipative system. Right, dissipative is actually a research-based discussion. Okay. So for this chapter, remember, is a mathematical procedural. You have to follow the procedure in order to make progress in your calculation, and then you have to go through. Let me set up this system again. My computer go in and out. Okay, so give me a few minutes to set up this. Okay, done. So any more questions related to this chapter overall? Two groups on a group project related, but on a very calculus. So I don't think you know to use the internet is not stable. Okay, let me just go. Seems to be okay. So just go through a particular system, any system, in any system. Okay, coordinate UK, and then PK, and then number 2, learn to calculate your T minus U, and the Hamiltonian is the T plus U. If you follow this route, the equation of motion for the Lagrangian is in QK minus d over dt d q dot k equals to 0. If you follow this route, so you have equation of motion is qk equals to, in terms of pk, and then you have the pk. So you have your pk dot equals to minus dh bar dp qk. Okay, so you solve this, at least you move in this, you solve, and you solve this. Okay, so if you solve this again, you get your qk, and then you can also determine your qk dot. Okay, so this is known, you solve, right? How does it change over time? And then you solve this also, you see you have qk, you solve and you get the pk. So these are two of these are connected. Okay, these two are connected. These are equivalent representation. So you can actually determine pk from Lagrangian qk. Okay, So you have this connectivity. So whatever you see on this page now essentially is your toolbox. Okay. So for every system, this is what you need to look at. So you probably have to identify conserved quantities. Okay. Conserve. Okay. Conserved quantities. Why conserve quantities? Because essentially, conserved quantity is an interesting property of a system. Why it doesn't change? Okay, so that is ultimately that you probably want to explain, and maybe how does it move, how the particle moves, and so on. Okay, so this chapter is essentially about this thing what you see on this piece of paper. Okay, anything else, the structure and so on, is just to bring some discussion point for the deeper deeper exploration of the topic, for those who would like to go into the foundation of mechanics or quantum mechanics. Okay, all right, so we have one more chapter in the syllabus, that is the relativity. So I will not discuss on relativity because you have already discussed some aspect of relativity in your modern physics. Okay, and it won't do justice just to repeat that again and then on a flyby. Okay, and I think you probably will explore more if you go into relativistic quantum mechanics course or your general theory or special theory. You will once again you will be exposed to that. So you can read the chapter which I attached. Okay, which I attached. So I will end the lesson today with this particular note, up to this point. And then another short chapter on relativity. If I have time, I will just do another Zoom notes and upload. You can read for the sake of completeness of the syllabus, the concepts like length contraction, time dilation. How does the kinematic variable position and momenta are changed to relativistic forms and so on. Okay, so I think that is an optional for this semester. You can read up. Okay, all right. So I'll give you a leeway for you to focus on the group project. Okay, on the group project, I'll put up. In fact, for the mechanics, you can look into the questions from the textbook. You try to solve that in a textbook, and few other examples that you may find on your own. Okay. For this chapter is very much problem solving scenario. So so there will be no class on Wednesday, because I want you to give you some time to really put some effort on your group discussion. Okay, for the group project. Okay, so take that opportunity. I know you guys have a lot of last minute assignment given by many courses. So for this course, I will end the course content delivery today. So next week, this Thursday, Wednesday, and next week, I give you the opportunity for your group to discuss and finalize the group project. Okay, and the time, during that time, you can use that time to email me the specific question related to the project. Okay, so that you can refine your project, the group project. Okay, so dedicate that time to discuss with your group members, and also to communicate with me via email. So I'll check the email about that time. I'll check the email and respond to your queries related to projects on the presentation formats, video formats, and so on. Okay, so I think that will relax you from a little bit burden on the coursework related, and let you focus on the remaining part, that is the group project. Okay, is that all right? Is that okay?
Highly appreciated, Doctor.
Okay, so you have time to use this to finish up whatever remaining task on the group project. It's a heavy assessment. It's not complicated, depends on how you see it, but it's a bit heavy in the assessment marks. So try your best to do something without too much of cut and paste, but simple but original, and demonstrate that you actually bring everyone in your group to participate. Okay, some may wish to just take advantage, but I think in life, people who take advantage on others eventually will pay in one way or another. So, so we just take this lesson in life. You have to earn, what you get, and it will last longer. Okay, so work in a team and finish up. We use that this Wednesday and the next week for any any queries and so on. I will answer through email. So there won't be Zoom session unless it's really necessary for some reason. Okay, I'll let you know. Okay then. So enjoy and keep me updated on whatever matters related to the course via email. Okay, and check the spectrum time to time. Okay then. So I'll end the class now. Okay, see you all.
Thank you, Prof.
Okay, bye.
Thank you, Prof.
Okay.